Isn't it good to see all of you again here? Um, so today what we will learn, we will cover the Mueller effect. So this is part 1 of the video. So let's get to this. To begin with part 1 of the Mueller effect, let's first figure out how this series lecture will work. So it's a two-part series. The first part is technically all of the prep work that we need to analyze. Then part 2 we will talk actually into the Mueller effect. So in part 1 we expanded our happy pi model because now we consider all the internal component, internal resistance and capacitance inside the transistor. We will study the short circuit current gain and the cutoff frequency due to those components. Then we will examine the Mueller effect and the physical origin of the Mueller effect. So first, we have to expand our happy pi equivalent circuit because now we need to add all the internal capacitance into the model. So far we consider our BJT was perfect, right? However, as you know, we have been ignoring the internal capacitance and internal resistance inside the transistor itself, which can influence the high frequency response of the circuit. So as you can see, I've given so this is your normal BJT, right? In manufacture, you actually have to have different layer of N-dope and P-dopes in semiconductor, typically silicon. So if you look in here, for example, the substrate is a P-type substrate with an N plus ferro layer, okay? And between, for example, between the B and C in here, there's a junction, right? That junction can actually have some capacitance between them, because what is capacitor? Capacitor is technically two conductive plate with an insert of dielectric, so the junction can act as a dielectric also as a certain condition. And also here you can have a capacitor, okay? So in the next few slides we'll understand what is those capacitors playing in the architecture of our transistor. So for example, this capacitor we can call it C pi, and this capacitor we will call it C mu. So first let's examine the BE junction of the expanded model. So here I have given you the expanded model, okay? And now if you look in here, there's a lot of new component, okay? You have an external component, the R external, you have the RB, you have the this is the original one, R pi, and you have an extra component in here, C pi. First, the R external. The R external is basically, if you look at this in here, this is basically the resistance between. This is the resistance between the internal base. The internal emitter terminal or internal emitter region, and the actual E terminal or emitter terminal. So if you can, there's a very small resistance in here. You can assume that to be 0, but for the sake of being accurate, we should put a resistor in here. So next is going to something more important. We have what is called the base. So the internal base resistance. So this is the base series resistance between this external base terminal, and the internal base region B prime. So I can connect a serial resistor in here. Then that will be labeled at RB. Next is the capacitance between the internal region B prime and E prime. So between here and here, so there's a junction, right? Therefore, you can actually examine the capacitance between that junction. So you add it in here, you can note that as C pi. And finally is our good old R pi. Okay, and R pi is basically the forward bias junction. This diffusion bias for R pi is forward bias junction diffusion resistance. And R pi is technically the resistance across this junction E prime and P prime in here. Next, we have the expanded hyperpi model or the CE junction. Even though it's not actually a junction because it's not neighboring each other, however, there's still some junction effect in here, and as a consequence, you can have some resistance and capacitance from the junction. So let's see what's going on in this hybrid model. First thing is RC. RC is the collector series resistance between C and C prime. Okay, so it's the resistance between here and here, the collector terminal and the internal region of the collector. Next is CS, which is the junction capacitance of the reverse bias collector substrate. That means it's the capacitance between the inner region of the collector and the substrate itself. And as you know, the substrate, you can treat it as ground. That's why we have a ground in here. And lastly is just the capacitance between the internal region of collector and emitter. So it's the resistance across here and here. And this is mostly due to the early effect. And finally, we're gonna consider the B and C junction. So between B and C, technically you can put in consider the resistance in this junction and the capacitance generated between this junction. Therefore, you can call this one R mu and this one to be C mu. And that's how you have an extra component in your expanded model in here. So if you put everything together from the original hyperpi equivalent circuit, you can have the expanded version with all the new components such as the external at between the inner region of emitter, then the emitter terminal, the C pi, the RB, the RO, the CS and RC. So you need to add in all of this new component in due to all of the internal effect. We can begin to understand the frequency effect of BJT by determining the short circuit current gain after simplifying the hyperpi model. So in order to simplify the hyperpi model for short circuit current gain, as suggested in the name short circuit, you need to sort it out a bunch of things. So you need to sort it the parasitic resistance. So basically all the resistance between the terminal and the inner region, you have to short circuit those resistance. So RB, RC, REX, cancel them out. Then you sorted out the BC diffusion resistance, R mu, sorted out the substrate capacitance. So because if you do this, you will effectively ground it the collector signal. And finally, you must make sure that or assume that the transistor still is still biased in forward active region. And finally, with all of this, you can have this simplified hyperpie model for short circuit current gain analysis. Then you can determine your current gain by finding the ratio IC, which is this current, over IB, which is this current. So the current coming into the base and the current coming into the collector. So after simplifying the hyperpie model, now we move to the next step to determine the current gain. Since we are trying to find a relationship between two currents, the K-cup current law will come in very handy here. So first, let's use the K-cup current law at the input node. So after apply that, you can have the current IB coming in coming to this node equal to on of the other current that come to this node B. So what is the other current do we have? We have the current going through this resistance here, so V pi over R pi. Then we have the current coming through this capacitance here. So you see, likewise, you use Ohm's law. It's gonna be V pi. It's gonna be V pi over. Sorry, I was talking about this one first. So the current coming through from here to here would be V pi. Okay, V pi over the impedance of this capacitance, which is 1 over j omega c pi. You do the same thing. Okay, since this signal is grounded, okay, C is actually ground, and so actually the voltage across here and here is also V pi. So you do the same thing, have V pi over 1 over j omega c mu. So you sum them up and you have the relationship. So now you just have to factor out V pi and you can have this term. So next, apply the KCL, K-cup current law, around the output node. You can have IC over IC, okay, equal to GM V pi plus not this, but this one plus C mu V pi over 1 over j omega c mu. Minus. So now you have actually with this you want to factor out V pi. Okay, after having V pi factor out, now you have a function for IC, then you have a function for IB. Both of these functions are in terms of V pi, right? So you can divide one for another and cancel out V pi, and this is what I'm gonna do here. I'm gonna figure out my current gain, and another terms for current gain is HFE, and this is in the H parameter node. You can look it up. But now I have the expression for my current gain. Oops. Sorry there. Messed up with a little with the animation, but in this current gain, in this expression for the current gain, if I plug in the typical value for C mu, okay, and how do I, the reason why I can use typical value is because this C mu coming from internal of transistor. So if the typical value is 0.05 picofarad, and I plug in the typical value for GM with a max frequency of around 500 megahertz, I can have the omega c mu to be a lot smaller than GM. Okay, so if omega c mu is a lot smaller than GM, then I can effectively cancel out this term. I can assume that to be 0 and cancel out this term. then I can estimate my current gain to be this. And what I did is basically I cancel out this term, I multiply the top and the bottom by r pi, and I have this. So now we have gm r pi here. Gm r pi is actually equal to beta, and this will be your low frequency gain. So now we have so we know the expression for the current gain. We know what's the current gain at low frequency, the magnitude of the current gain at low frequency. So we can draw the body plot. So it looks like this. It's low pass, more like it looks like a low pass filter with the current gain of beta. Okay, as we discussed. So so this curve is the actual curve, and this is the body plot. So at the corner frequency is actually 3 dB lower than the maximum current gain, and this corner frequency you can calculate that by so f beta is the corner frequency. You can calculate it by 1 over 2 by tau beta. Tau beta is the time constant of that circuit. It will be 1 over 2 pi. The time constant will be equal to r pi multiplied by c pi plus c mu. For the phase plot of the current gain, as the frequency increase, a small signal collector current will no longer in phase with the small signal of the base current. So at a very high frequency, you can see in the farther end of the frequency spectrum in the phase plot, the collector current lags of the input current will be lagging by 90 degrees. So this beta corner frequency is also called beta cutoff frequency. Another frequency of interest today is going to be the FT cutoff frequency. If you notice, this FT is basically the gain, the current gain when is equal to 1. So this is where basically there's no more gain happening. The input current and the output current equal to each other. So let's try to derive this FT cutoff frequency. So if I have my current gain, or I can use just another term for it as HFE, I can express that in terms of F, right, instead of omega. So I can write down my equation like this. So I can, this is a complex number, so I take the magnitude of this complex number. I have this function. I assign it to be equal to 1 because I want to find the frequency that make the whole magnitude of the current gain to be 1. So I assign for 1, and I solve for F or FT. Okay, I can do that a little bit complicated, but I can make the math a little bit simpler by using the fact that beta is pretty large, right? Usually it's over 100. So if beta is very large, you can imply that FT is a lot larger than FB. As you can see in here, the cutoff frequency is usually a lot larger than the beta frequency. So if FT is a lot larger than FB, then FT over FB is a larger than 1. Then if this is a lot larger than 1, and you also square it, the value of this term will dominate this term, right? So you can cancel that out too. Therefore, you are left off with basically square root of F over FT over FB F beta square. You cancel out the square, and now you have left with this. And you can estimate that to equal to 1, then you can solve for FT easily. So now I have my equation for FT to be beta multiplied by f beta. Okay, some fun fact here. So this beta corner frequency or beta cutoff frequency is also called bandwidth of the transistor. Why? As you see in here, it's literally the bandwidth that allow the current to gain maximum in the maximum value. Why this FT is called unity gain bandwidth. So one thing to notice before we end the lecture today is all of this short circuit gain and cutoff frequency, short circuit current gain and cutoff frequency is pretty much applicable for most of the application until you are interested until you are interested in operating your transistor in the microwave frequency. In that case, the order of FT or the cutoff frequency will be around 10 gigahertz. If you're operating your transistor in that regions, then you need to put off the parasitic element and into your model, because that will start counting. So that is it for today, guys, and I will come back with part 2 of the series. Okay, so we have finished the first part of this series. I will see you guys next time in the second part. Bye!